Afternoon, friends. Myself, Rishikesh Mishra, Rajaramana Fellow, DAE, and I welcome you all in today's lecture, which is 48th lecture in the series on radioactive waste management. Before we begin the discussion on this topic, I have few small things to tell you. That first of all, my heartiest congratulations to all of you for making a successful mark in our stage one program on disaster management course. You have all really fared very well in the examination, and we are very glad for that. Certificates are ready, and the moment we compile all the addresses of the various successful participants, we will be dispatching the certificates to you individually. And while on the topic of examination, I propose that we will be conducting the exam for stage two, of course, on completion of this course during first week of April. So we can have the exam either on 5th of April or 8th of the April. And exams will be conducted in the same way as it was done for stage one. Secondly, during the last week, we'll have a question answer session also, most likely on 1st April, we can have that. And we will have seminar also, and format for the seminar will be decided very soon, and we'll inform you. That will also be during the concluding days of the course. We'll come back with all the details on seminar and the question answer session plus exam shortly with you. So here I think we begin the discussion on today's topic on radioactive waste management. Slides, huh? Prajapati? Sunny, it's not moving. Yeah. So topics for discussion in today's lecture are application of nuclear energy, that is more on the outreach of the nuclear power system, nuclear energy. Radiation fundamentals, we will discuss some more things, some more slides on this topic. The generation of electricity, nuclear power plants, and then we will take up radioactive waste management. So to begin with, the nuclear energy has application in various fields. So Baba Atomic Research Center and of course Homi Bhabha National Institute, HVNI, we are busy and we are working in the field of research and development in agriculture, medicine, electricity, industry, science and research, and national security. So the nuclear energy has application in all these fields. You know that agriculture, a lot of research is being carried out for development of new varieties of seeds. In medicines, we have a very, very big role in treatment of cancer plus in diagnostics. Electricity generation through nuclear power plant is a well-known thing. We'll have few slides on that topic today. And atoms have applications in industries also. You know, the radioisotopes, they are used for various applications for radiometry, plus electron accelerators are used for irradiations purposes. We are also planning to have some EV, that is electron beam based irradiation systems for sewage treatment, for wastewater treatment, for tannery waste water treatment, and so on. In national security, you know that the nuclear energy has a very defined role. Plus, the fundamental research is carried out in BRC in nuclear energy. So, the electricity needs of India. In this slide, you see that per capita income, per capita consumption of electricity in India is just about 704 as compared to the per capita consumption of electricity in USA being something of the order of 13,616, in Japan 8,475, and the world average is 2,752. So there is a huge gap, and it is also said that quality of life go in comparison with consumption of electricity, but they both are related topics. The quality goes up if consumption goes up. It is said so to be so, and I believe it's so. So there is a huge scope for further improvement on our front. If we can have the per capita consumption at least up to the world average of 2,700 plus, I think we'll be better off. And for that, the generation has to be improved. Whatever is the generation today, that has to be at least increased 4 times to match with the figure of per capita consumption. Now, here we have a comparison of electricity generation from a nuclear power plant or from a thermal power plant. So let us see if we have a 1,000 megawatt nuclear power plant, a combination of nuclear power plants versus the 1,000 megawatt coal-fired thermal power plants. So you see the figures, the land required for nuclear power plant will be about 20 hectares as against 70 hectares required for a thermal power plant. And fuel requirement, there is actually no comparison. All the nuclear fuel required for this much capacity is 160 ton per annum for a nuclear power plant. It is 2,600,000 ton per annum for thermal power plants of that capacity. There is absolutely no comparison between these two. And you see the emissions from a nuclear power plant, emissions are negligible. Of course, it is not there. It is, if at all it is there, it is due to the auxiliary systems. But in a thermal power plant, we have CO2, SO2, and NOx emissions. which are very, very huge. The figures are given here. And if you talk about the waste, the nuclear waste comes out to be less than 1 ton per annum, while the waste from coal plant, coal-based thermal power plant, is to the tune of 1.2 million ton per annum. That is in the form of ash. And the picture, whatever figures I showed you in the last slide, the same thing is represented here in form of a picture, that for 1 million units of electricity generated in nuclear power plant, we require basically just 2 fuel bundles, each weighing about 27 kg, natural uranium, in our PHWR power plants, that is pressurized heavy water reactors. In pressurized heavy water reactors, which we have in our country, which we have mastered the technology completely, right from the research, design, development, construction, operation, maintenance, and even refurbishments. So there we require just 2 bundles for generating 1 million units of electricity. While in thermal power plants, the requirement be to the tune of 700 tons of coal for generating that many units of electricity. That is kilowatt hour. And what will be the effect? You see, there are no emissions from nuclear power plant in the form of CO2, NO2, or NOx gases, SO2. Now, from the thermal power plant, when these gases are emitted, what we see is the greenhouse effect, which results into the warming of the Earth's surface, warming of the total atmosphere. Because these gases trap the energy, trap the heat, and do not allow energy to escape to the space. And that is how the temperature goes up in and around us year by year as the time flies. So that is the greenhouse gases trap heat, leading to global warming and change in mean sea level. And the result is in the form of impact of fossil fuel on the climate. We get the floods, we find the glaciers receding continuously on our Himalayas, and this global warming results in a change in mean sea level by 1 meter, will devastate India's coastal landmass. A lot of cities may get submerged if this trend is not stopped. How the electricity generated in a nuclear reactor, that is represented in this slide. We have the nuclear heat, that is the heat produced in the chain reactions of nuclear fission. And that heat is used to generate the steam. That is, steam drives steam turbine drives generator, and the electricity is produced. That is a very, very simple representation of the scheme in the form of a block diagram. And we discussed this earlier also. We have types of reactors in our country. That is boiling water reactors, pressurized heavy water reactors, pressurized water reactors, fast breeder reactor, and advanced heavy water reactor. Of course, that is not there in reality as on today. That is still in design. And fast breeder reactor, we have fast breeder test reactors at Kalpakam, and prototype fast breeder reactor is coming up at Kalpakam, 500 megawatt unit, 500 megawatt capacity at Kalpakam, which may be ready very soon. So this picture is about the pressurized heavy water reactors, PHWR. We have at several sites in our country at Tarapur, at Rajasthan Kota, Kakrapara, Kaiga, Kalpakam. So you see in the core, the nuclear reaction takes place, fission reaction takes place, and the heat is removed from the fuel bundles in the in the place in the coolant channel of the core through a primary heat transfer system, and then we have the steam generators, and the steam generators, then the steam is produced, and that is steam is used to drive a turbine. Turbine drives the generator. And you will find that the primary heat transfer system, the core, everything is placed in a containment structure. So there are dual containments. Basically, it is to improve the safety. So the nuclear system is very well contained within the containment systems. The idea is that radioactivity should not get released to the environment or even to the plant. So it is confined to the basically reactor building only. So this slide we had seen earlier also. See how multiple barriers are provided. We call it defense in depth. Idea is to, safeguard, safe to make our system as safe as possible so that there is no risk of any emergencies, no risk for the radiological emergencies. Idea is that radioactivity should not be released to the environment. So for that purpose, multiple barriers are provided in a nuclear power plant, particularly in our design. And these barriers may be ranging right up to, in fact, 8. Though in this slide it is shown just as 6, but there may be some 8 multiple barriers. That is in the form of the pellet first, pellet, that fuel bundle, whatever picture I showed you a little earlier, that fuel bundle actually contains number of fuel pellets. And that is one barrier. Then the cladding, zirconium cladding, all those pellets are pushed into a cladding. Then cladding is placed in the coolant channel actually, that is shown in the red color, which is flooded with the coolant, and primary containment building is there for, then the secondary containment is there through the reactor building, and we have exclusion zone for safety of the public. But there are many other barriers provided, which I am not telling here. That is in the form of various other systems. In subsequent lectures, you will see the details little more in detail. This is our three-stage nuclear power program. India's three-stage nuclear power program. So basically, idea is to utilize country's vast reserves of thorium. That is our aim. So how we go about that in the stage one? We are actually we have already mastered the stage one, and now we are very closely working on stage two. So in stage one, we have PHWRs where we use the natural uranium as fuel, and from the spent fuel, when the fuel is used in the reactor, what is left out is the spent fuel. We call it actually spent fuel, but as I mentioned in my previous lectures, it is still contains very, very useful isotopes like plutonium. It is still contains depleted uranium U-235. So that can be reused and they are recovered. This uranium and plutonium are recovered in our reprocessing plants and which can be used as a fuel for fast breeder reactors. We are already using that in FBTR. And in FBTRs, we use this plutonium and thorium as blankets, and thorium gets converted into U-233. And these are breeder reactors, so they further breed the plutonium. So whatever, I mean, U-238 is converted into Pu-239. So that is also reused or rather participates in the nuclear reaction in the fast breeder reactors directly. And whatever U-233 is generated, that is to be used in our stage 3 reactors, which will be U-233 based breeder reactors, where again thorium will be used as blanket, which will get converted into U-233, and that breeder reactor will continue producing electricity. Our estimates show that we can generate something like 12 gigawatt electricity from stage 1 reactors, about 200, 300 gigawatt from stage 2 fast breeder reactors, and 500 gigawatt from stage 3 U-233 fueled reactors, breeder reactors. Same thing is shown in this slide. I think I'll have to go a little faster. So stage 1, stage 2, stage 3, same it is shown. The three-stage nuclear power plant program ascertains optimal utilization of uranium and thorium resources. We have plenty of thorium resources and we aim to use those resources for generation of electricity as efficiently and as soon as possible. We discuss the radioactivity now. So radioactivity is actually there in our life on an everyday basis. What is established fact? What is the established fact that bananas are containing potassium 40, which is radioactive. But it is not harmful. You all would agree with me. Air travel, they are also from the cosmic particles, cosmic rays, we are exposed to some kind of a radiation. But it is all still very safe. There is nothing to get warned about it. When we are climbing hills, then also we are exposed to cosmic rays. We are exposed to natural radioactivity also. So radioactivity is part of our life, you can say. Radiation is our friend. It is there and it is very useful. We had seen in the previous lectures also that there is a natural background to the tune of 2.5 millisievert per annum a man gets from the nature without actually having anything to do with it, without having to do anything with it. You get it. You like it or you don't like it. That is in the form of radon. From the air, we get 51%. From the food, we have seen that banana contains potassium 14. Like that, there are other foods also which contain some kind of radioactivity. So food, we get 12%. So natural and of course terrestrial 14%. So nature's contribution to radiation exposure is to the tune of 87%. Then we get radiation from medical treatment, from various kind of fallouts, from the occupation. Some people are engaged in activities where radiation is there. So that percentage is just about 0.2%. And from the nuclear activities, nuclear program, the exposure is only 0.1%. Negligible, of course. Existence of human civilization in radiation environment. So what we find that from food it is 12%, cosmic rays 10%, terrestrial 14%, radon 51%. So whatever was shown in that slide, it is tabulated here. And this is not something which I am saying. It is all very well documented, very well recorded, and there is a reference available that is from safety report series of IAEA, Managing Nuclear Safety Knowledge, National Approaches and Experience. And what we see the natural high background areas around the world. In India, well, you all would have heard about it, that we have monazite sand at Kerala sites. And dose is something like 15.7 millisievert per annum. But it doesn't cause any harm to anybody over there. This we have seen from millions of years. Nobody has ever complained that monazite sand has been harmful for them. Brazil at Gorapari, it is 24.5, again from monazite sand. And China, Yangziang, 3.2. Iran, Ramsar, 7 to 35. And Italy, in Orevito town, 4.9 dose is there from volcanic soil. No complaints as yet. And another comparison, how we get radiation. So comparison of risk in various scenarios at a glance, that is how the radiation may be causing cancer. So various analysis have been done, various data has been collected, and it is documented that if a person if people smoking some 20 cigarettes per day, then there could be one death in 200 per year. So that is said to be around 31%. And deep sea fishing accidents, nothing about the cancer. Deep sea fishing accident, it is 1 in 400. Natural death beyond 40 years or up to 40 years, 1 in 500. Accidents on road, 1 in 5,000. Accidents in home, 1 in 10,000. Accident at work, 1 in 20,000. And radiation work, that is chance of death per annum in the radiation work, those who are working in the radiation field, and if they get a dose of the order of 2 million sievert per year, 2 millisievert per year, then it is 1 in 20,000. So if 20,000 people work in a nuclear plant, and if they are exposed to a radiation of 2 millisievert per year, there could be maximum one death. That is how it is documented in the safety report series of IAEA. It is not my figure. So what we are trying to say that working in nuclear plant is absolutely safe. When the study shows that it is 2 millisievert per year, actually we ensure that our people are not exposed even to that limit. And the other picture shows the cancer causing due to various reasons. So cancer may be caused due to various reasons. So from the food itself, in fact, cancer may be caused. That reason could be 33%. In smoking, it could be 31%. And hereditary also, it could be 2%. Those who consume alcohol, they are at the risk of about 4%. Then the viral infections, unknown figures are there. So, but from the industrial occupation, that ratio works out to be around 4%. Radiation hazards, we continue. So, what are the hazards? Annual occupational dose for various jobs. So, you will find that in the nuclear power plant, it is just about 2.5 millisievert per year. Maximum limit is 20 only. And air crews, it is 4. Medical personnel, 0.5. Mining, it is 6. Industrial radiography, 1.5. In the research plants, it is controlled at 0.8 millisievert per year. The external hazards, they are content controlled with the help of formula, well-established methods, that is time control, distance control, and shielding. And internal hazards are controlled through contamination control. Contaminations not to be allowed to be there. And guideline is based upon IAEA report on human and organizational factors in nuclear safety in the light of accident at the Fukushima nuclear power plant. This is the guideline or safety report available on that. Now the today's topic is radioactive waste management. So management of radioactive waste, a key component. If we go by the guideline set by Dr. Homi J. Bhabha sir, that is radioactive material and sources of radiation should be handled in atomic energy establishment in a manner which not only ensure that no harm can come to workers in the establishment or anyone else, but also in an exemplary manner so as to set a standard which other organizations in the country may be asked to emulate. So the first thing is that there is no harm to worker or even to anyone else, definitely not to the public. And then to establish standards which can be emulated by the other industries. So that is the principle laid down by our Dr. Homi J. Bhabha, sir, founder of Nuclear Power Program in India. And when we work on the radioactive waste management plants, the principles are recycle and reuse, waste volume minimization, and near zero discharge of radioactivity to the environment as Mool mantras. The picture on the right shows one of the nuclear waste management plant. Now, the generation of waste. So this is an established fact that the human civilizations, in fact, all industrial activities give rise to the some unwanted byproducts, which are called as waste. And it applies to nuclear industry as well. In countries with nuclear power, radioactive waste comprises less than 1% of total industrial waste generated. But it does mean that the total waste volume of a country where the nuclear power plants are there or nuclear facilities are there. So it is found that the contribution of nuclear waste is only 1%. The other waste are 99%. And of course, other waste, since we are talking about CBR and emergency challenges, I should not say just chemical waste, but this picture shows that chemical waste hazards are forever, while the nuclear waste hazard potential gets reduced with time. Yes, we know that radioactivity decays. All those radioisotopes have a half-life. This we have seen in the previous slides, previous lectures also. So if cobalt source is there, it will lose its radioactivity strength over the time. So that is how the hazard potential gets reduced with time. Whether that applies with chemical waste, I will not say anything, but this slide says that hazards are forever. Now the objectives and philosophy of management of radioactive waste. We have seen this in the earlier lectures also, that basic tenets are delay and decay. If there is a very, very small negligible kind of radioactivity in the form of beta gamma activity, which has very short half-life, then we will delay its disposal and will allow it to decay. Wherever it is negligible radioactivity, exempted waste kind of thing, something like BDL, below detected limits, below detection limits, so it can be discharged at near zero discharge facilities. And whenever it is high radioactivity, we have to concentrate, its volume has to be reduced, and it has to be contained well within the institutional system. We'll see more in details little later. Principle of reduce, recycle, and reuse will apply wherever we are able to remove and recover the radioisotopes. We will try to recover that and we will try to reuse that, recycle that. That you have seen. Uranium, plutonium, we recover and we try to reuse. Or we recover cesium, ruthenium, etc., and we use it for various applications in the industry or in the medical field. Idea is basically the management is objective is the protection of human health, environment, and future generation. Now, the volumes in the radioactive waste management, we have three categories basically. So radioactive liquid waste basically has been broadly categorized into three categories depending on the concentration of radionuclides. So that applies for liquid waste. So there are three categories, that is low level waste, which is less than 1 millicurie per liter, and its volume is 90%. Then intermediate level waste, ILW, when activity is between 1 millicurie to 1 curie per liter, volume works out to be around 7 to 8%. And high level waste, activity always more than 1 curie per liter, and that volume is found to be less than 2%. In fact, it is just about 1%. And of course, we have the liquid waste, solid waste, and gaseous waste also of combustible or non-combustible type, compressible or non-compressible type also. We'll see little details further. This we had discussed earlier also. So radioactive liquid waste, how we treat when radioactivity is less, then we try to, reduce the volume. We reduce the volume in such a way that volume is drastically reduced. And of course, radioactivity level will be same. That applies for the very, very low level liquid waste. And when it is high level liquid waste, then we try to reduce the activity by recovering the radioisotopes. So activity is drastically reduced, volume is more or less retained. That is the basic principle of radioactive waste treatment, where management strategy. And waste management is actually a hybrid science and technology, where we have separation chemistry, material chemistry, nuclear chemistry, spectroscopy, thermochemistry, and all types of technologies are used in the field of nuclear waste management. That is chemical, mechanical engineering, glass technology, electrical and electronics engineering, and robotics engineering also. All these technologies and science are applied in the treatment of nuclear waste. So waste characterizations for physical, chemical, and radiological things. So radioactive waste, first it is pre-treated, then treated, conditioned, and finally disposed of. Nuclear materials are recovered, recycled or reused, and whatever negligible exempt waste is there, which is disposed to the environment. Now we talk about the gaseous waste. So we use HEPA filters. We use chemical impregnated activated charcoal. So these HEPA filters are high efficiency particulate air filters made of microglass fibers. So wherever gases are generated during the process, they are actually passed through these HEPA filters. So all radioactivity particulates, whatever particulates are there, they are actually captured. They are not allowed to be passed through the filters. And then the clean air is finally disposed of from our towel stacks, so that in the environment, radioactivity is not really released. And then we have absorbents, something like nickel sulfide coated alumina. We call it chemical impregnated activated charcoal, which can absorb the radioactivity like ruthenium-106. So idea is we dilute it by removing the particulates and finally allow the dispersion after delay and decay. Low level liquid waste treatment methods. So, no, sorry, low level solid waste treatment methods. So here we have the principles like compaction, combustion, and melt densification and incinerations. The plastic and rubber, which can be compacted, so we reduce the volume. The combustion, whatever cellulosic waste is there, that is combusted, burnt, and melt densification, where volume can be reduced. So that is polythene, which can be densified. And then category 1 solid waste are there, which are incinerated. So we have developed some new types of incinerators, which are plasma assisted. So here we are a volume reduction factor of the order of 30 to 40 is achieved. So the non-treatable waste are directly disposed of, which of course will be very, very low radioactive in the strength of radioactivity. Then we are talking about the solid waste. So whatever low level radioactive solid wastes are there, they are disposed of in the near surface disposal facilities. And this is our own facilities actually. It is not there in the public environment. This is well within our campus, in our own site. And we take full measures for safety of these sites. And what we are disposing of is only actually the low level radioactive waste. The multi-barrier concepts for isolating surroundings and control the radioactivity released to environment is followed. Then low-level liquid waste treatment, that is in the form of chemical precipitations through coagulation and flocculations, ion exchange through polyurethane, PU, it is not plutonium, it is polyurethane, foam coated with Cu ferrocyanide and hydrous manganese oxide as exchanger. Basically, this helps in, recovery of radioactive systems like radionuclides like cesium or strontium, etc. And then reverse osmosis for waste containing low solids. So we use membrane, spiral type or so on, this type for recovery of certain radioisotopes. Near zero discharge of radioactivity to the environment. That is, of course, the principle. Now, understanding the ion exchange mechanism by hydration theory. So, RF resin granules release sodium and absorbs cesium ion, for which it has a greater affinity. Ions are not destroyed or changed chemically. They are simply replaced on the RF resin granule. This process is known as the ion exchange. Actually, in the next lecture, which is there on 6th, this thing will be discussed in detail by our Dr. Kaushik, CP Kaushik. Now, the near nuclear waste storage and disposal, that is about the high-level waste. So high-level waste that is in the form of liquid, which is mixed with the liquid glass. It is heated up to the temperature of about 1000 degrees Celsius. Then it is poured in the containers, canisters, and they all are remotely handled. That's why I said robotics engineering is applied in the waste management systems. This entire operation is carried out in a highly sealed, biologically sealed cells, we call the process cells, and all operations are carried out remotely with the help of manipulators, cranes, and other robotic tools and instruments. So then it is welded also. Finally, of course, it is to be stored in deep geological repositories, but right now they are contained in our own facilities in air-cooled storage systems. Nuclear waste. So finally, it is immobilized, that is, it is mixed with the glass, and then it is allowed to be cooled so that it gets vitrified. Then there is interim storage in our air-cooled storage. And finally, is it will go into the deep disposal facilities, maybe after more than 50, 70 years. Wealth from nuclear waste. This we had seen in the last lecture also. So from the spent fuel, we are able to recover uranium and plutonium in our reprocessing facilities. And from the waste, in the waste management plant, we recover cesium, strontium, uh, technetium, neptunium, americium, and so on, transuranics, and how they are used in the various fields in the industrial medical field. We'll be discussing more in details in the next lecture. So reprocessed fuel, that is spent fuel, and radioisotopes are like this. Thank you very much. Thank you for your time. Any questions? Yes. 15th April, we had originally proposed, but there is a little constraint. So we are proposing to prepone it by 1 week. If it is not inconvenient to you all, I think we would do so. So in fact, we thought of preponing to 5th April, but another alternative I'm proposing is 8th April. So if 8th April is okay, we will work it on this. We'll finalize as 8th April. If you have any problem, please let me know. What was the last question? This last class, when is the last class? When is the last class? Yes. So last class will be there roughly on 29th March. Though we'll have invited talk on 3rd April. We'll have a seminar maybe on 1st April. And we'll have question answer session on 5th April. So for all practical purposes, I'll say last class will be on 29th March. I will be modifying the schedule. Some of the lectures are not listed down in the schedule so far. So by this weekend, I think I will modify it and make it final. Any other question? So, madam, if we consider that 29th March is the last class, so hopefully by 8 we get around 10 days. So if you all agree, we'll finalize as 8th April as the date for exam. Otherwise, maybe I'll try for 10th April. So please tell me, 8th or 10th April. One of these two dates I'll finalize. You can write to me later on, write to our help desk. Okay. Thank you. Thank you for today's lecture. We'll meet again soon, shortly. Thanks.